Imagine this situation. A customer places an order. The system charges their credit card, but the order never ships. The payment database is correct, the inventory database is correct, the order database is correct, and yet the system is wrong. This kind of failure happens in distributed systems all the time because data consistency is not actually a database problem, it's a systems design problem, and many engineers are still using the wrong mental model. For decades, application architecture looked like this. One application, one database. All business logic ran inside a single system, and every operation could be protected by a transaction. If something failed, the database rolled the transaction back. Either everything happened or nothing happened. Consistency was enforced by the database, and for that architecture, the mental model was correct. But modern systems are built very differently. Today, we split systems into services. Each service owns its own data. Each service commits its own transactions. Orders, payments, inventory, and shipping all have their own database. And suddenly, the business workflow spans multiple systems. The database no longer controls the workflow. Consistency becomes a property of the interactions between services. Let's go back to the checkout example. A customer places an order. The payment service captures payment. The inventory service reserves stock. Shipping prepares the delivery. Now, imagine the payment succeeds, but inventory reservation fails. The payment system correctly recorded the charge. The inventory system correctly shows that no stock was reserved. But the business outcome is wrong. The customer paid for something that cannot be shipped. Nothing is technically inconsistent in the data. The database didn't fail. The workflow did. One of the most common failure modes in distributed systems is retries. Retries are necessary. Networks fail. Requests time out. Services restart. When something looks like it might have failed, the system retries. But retries are dangerous when operations are not idempotent. Imagine a payment request that times out. So it retries the request. If the original request actually succeeded, the retry may execute the same operation again. Now the customer has been charged twice. The database did exactly what it was designed to do. The architecture allowed the mistake. Another failure mode is event ordering. In asynchronous systems, events do not always arrive in the same order they were produced. Imagine two events: inventory reserved, inventory released. If those events arrive out of order, the system may believe inventory is available when it is not. Or the opposite. Each service processes the events it receives, but the system logic now operates on the wrong sequence of events. Distributed systems can also lose messages. A service crashes while processing an event. A consumer fails before acknowledging a message. A queue retention window expires. Now, one step in the workflow never happens. Nothing in the database detects that something is missing, because nothing incorrect was written. Something simply never occurred. Concurrency introduces another subtle problem. Two services may update the same concept at the same time. For example, one process cancels an order while another ships it. Both operations succeed independently. Each service did exactly what it was designed to do. But the system ends up in a logically impossible state. An order that was canceled has also been shipped. This is the architectural shift many engineers overlook. Consistency used to be enforced by the database, but once systems become distributed, the database protects only local state. Consistency now lives in the workflow between services. And those workflows involve retries, delays, concurrency, partial failures, and asynchronous communication. The database cannot control any of that. That is why distributed systems rely on patterns above the database layer. Idempotency ensures retries do not create duplicate side effects. Sagas coordinate multi-step workflows across services. Event sourcing preserves the sequence of state changes. Reconciliation processes detect and repair inconsistencies after failures. These patterns do not make the database more consistent. They make the system resilient to failure. And that leads to the real architectural insight. Consistency is not a property of a component. It is a property of a process across components. Once a system becomes distributed, the responsibility for consistency moves from the database to the architecture itself. The database can guarantee that individual operations are correct, but it cannot guarantee that the system behaves correctly. That responsibility belongs to the design of the workflows between services. So the next time someone says the database guarantees consistency, remember this: the database can be perfectly correct, while the system as a whole is completely wrong. Because in distributed architectures, data consistency is no longer a database problem. It is a systems design problem. Architecture is deciding where the system is allowed to fail.